Hi friends, you must have heard of this. They say attention is all you need. But attention isn't just one thing. There's self-attention, multi-head attention, and more. So what exactly is attention? Why do we need it? And how do we get there? Today, we're going to break it down and explore three key attention mechanisms. Let's get started.
So, what is attention? Let's start by defining a problem. We use attention to handle sequential data that comes in sequence, such as text, speech, or time series data. But handling this sequential data has some challenges. First of all, sequential data don't always have a fixed length. Some sequence can be longer, some sequence can be shorter. How do we handle this variable length? And second of all, sequence has a number of tokens. So when you're modeling a single token, you must consider the context. The longer the sequence, the long range of contexts and dependencies you have to consider when you are modeling. And lastly, order also matters. Let's look at how people handle sequential data historically. The most ancient way is to use a feed-forward neural network. It treats each input token independently, so it doesn't handle order and has no memory. That is why RNN was invented. RNN handles the data sequentially by processing data step by step, where the output of one step is the input of the next step, creating a form of memory. But that also comes with a problem. It's called vanishing gradient. As the token size grows, a gradient shrinks or explodes during the back propagation, making the training unstable. Because of this, LSTM and GRU are introduced. LSTMs use forget, input, output gates to selectively remember and forget information. And GRU simplifies this process using reset and update gates. So these gates, they work together and achieve a similar result as gate connections in ResNet, but in a more granular and controlled way. Well, LSTM and GRU, they perform better than standard RNNs. They still process data sequentially and has limitations on parallelization and has difficulties to learn global context. Then, around 2014 or 2015, researchers introduced attention mechanisms. Traditional models rely on using final hidden state to make predictions. But this approach loses information from earlier parts of the sequence. Attention solves this by allowing the model to focus on relevant parts of the input sequence rather than relying solely on the last hidden stage. It enables the model to consider the entire sequence at each step, giving better context and improving accuracy. However, even with attention, RNNs and LSTMs were still sequential. This was eventually solved by Transformer, the architecture that makes attention famous. Transformer eliminates sequential dependencies by using self-attention and positional encoding instead of recurrence. This allows models to process all sequences in parallel. It largely improves the training efficiency. And Transformer is the architecture that is used in BERT, GPT, and DeepSeek models. Now let's take a closer look at attention mechanism. While attention might be complex at first, there's this powerful analogy that can help us visualize how it works, which is database. In a typical key-value database, you send a query to the database compares your query against stored keys. When a match is found, it returns the corresponding values as results. This is exactly how attention mechanism works, but with some improvements to make it suitable for deep learning framework. In attention mechanism, we also have three main components, which is query, what we are looking for, and key, what we are comparing at, and value is what we are going to retrieve when we find a match. In attention mechanism, the query, key, and value, they are all tensors and vector representations. Instead of finding the exact match, attention mechanism will calculate the similarity between query and keys. And finally, instead of only returning one match, attention mechanism return a weighted combination of values based on how similar each key is to our query. Let's walk through this process step by step. So start with the input tokens. We have the cat sits mat. The model creates vector representations and then use query key value projections to project each token into embeddings that represents query key and value. Here, we are making queries for token 2. This query vector will calculate how similar it is to every key vector by taking the dot product, and then after scaling the scores and apply softmax, we get the attention weights. And we aggregate the attention weights with the values. Now we get the attention results. So to summarize here, what makes attention more powerful than a simple database is that it does partial matching by computing the similarity between keys and queries. And it also does this weighted retrieval that has a combination of multiple values in this database. And lastly, for the query key and value, those are all learned parameters that can be improved throughout training. But in practice, we don't just use a single attention mechanism, but more sophisticated attention mechanisms. So here we're going to talk about a few common ones. First one is multi-head attention. Multi-head attention was first introduced by Transformer paper. In self-attention setup, you interpret each of your token into one set of query key and value. Multi-head self-attention extends this by projecting the same token into different sets of query key and value. So here, as you can see, for the same input, multi-head attention generates two sets of query key and value, and then it does concatenation and aggregation to get the final results. The benefits of multi-head attention allows the model to simultaneously attend information from different representation subspaces and make it more versatile and expressive. But multi-head attention is also very expensive. Imagine you are training a large language model. You have hundreds of thousands of tokens, and for each token, you need to have a set of QKV. This poses a challenge to the memory consumption at the training time and inference time. So what is the solution? The first solution here is called multi-query attention. The key idea of multi-query attention is to share key and values and only have the query have multiple ones. So basically, for each input token, you project this token into multiple queries, but all those queries, they share the same key and value. This way, your key value memory consumption doesn't increase increasingly with the number of your heads. It's a more memory efficient way, but also comes at the cost of performance trade-off. The performance trade-off is the reason why we have group query attention. Group query attention is how you can tune between multi-query attention and multi-head attention. The key idea of group query attention is that it has several groups of key value pairs. And within each group, you can have multiple queries within, and they all share the same key value pairs. So as you can imagine, if you have only one group for group query attention, then group query attention is equal to multi-query attention. If you increase number of groups to be the same number of heads, to be the same number of queries, then your group query attention is equal to multi-head attention. You can tune number of groups based on your needs for memory and performance trade-off. Here is a comparison. It's saying, like, suppose we have a model with 8 heads, if we have group queries with 2 to 4 groups, then using group query attention is able to save 2 to 4 times of the memory consumption for key values. And using multi-query attention consumes the lowest amount of memory, but also comes at the cost of performance. So in practice, I do see people use group query attention and tune number of groups based on performance and computation trade-off. So that's it for this session. We talk about the problem that attention solves. We talk about the intuition behind attention. And then we talk about 3 attention mechanisms, which is MHA, MQA, and GQA. So what's next? Next, we're going to talk about attention part 2, which is efficient implementations of attention. And for part 3, we'll talk about attention in recommendation systems. I'll see you next time. Thank you for watching.